Okay, so we'll continue our discussion. Um, here's our here's our Manning's equation for the velocity. That's v is equal to k all over n. We use k is equal to 1 if we're in SI units, or k is equal to 1.49 if we're using English units. K all over n times r, that's the hydraulic radius raised to 2/3, and this one is s, that's the channel slope raised to 1/2. Okay, so the hydraulic radius is cross-sectional area divided by this weathered perimeter, and if you check the units, this is meter squared, right? And this one is meter or feet squared, and then this one is in feet, and the unit for this should be in meters. And for channel slope, as I've mentioned, this is sometimes in terms of percentage or in terms of length per unit length. Let's say meters per meter, or millimeters per meters. Of course, we need to do the conversion, but let's say meter per meter. Then that's it has no units, right? So if we substitute, let's say we have a value of channel slope, we substitute it here, and we substitute this one here, then just don't worry about the units, because this is an empirical equation. So this must be the unit of velocity would be meters per second. Right, this one, this n, that's the Manning's coefficient, and that depends upon the type of channel or the material in the channel. So right here in table 11-1 of our lecture handouts, if it's a concrete, then the Manning's coefficient is 0.012. If it is smooth asphalt, then it is 0.013. If it's just an earth or gravel beds plus large boulders, then this is 0.04. So in other words, depending upon the material used in our open channels, that's going to be, I mean, there's going to be a value, a unique value, specific value of the Manning's coefficient. And whether we are solving in either English or SI units, we just use the same Manning's coefficient. Okay, so I guess we'll do computations. We'll try to do some computations, and we'll get some practice. Okay, so first problem that we have is from this textbook, one of our reference texts, Fluid Mechanics by Hibbeler, and this is example 12.8. It says here that the channel in the figure is made of finished concrete, and the bed drops 2 meters in elevations for a horizontal reach, or that's the length of the channel. That's the longitudinal length of the channel, stretch or reach of 1,000 meters. We are asked to determine the steady uniform volumetric flow when the depth of water is 2 meters. Right, so here it is. Here's our rectangular cross-section, rectangular channel, and it's a concrete. And the depth is 2 meters. We have this 3 meters bottom width, which is just equal to the top width. And here's our slope. So 1,000 meters along the length, and we have this rise of 2 meters. And we are asked to find the volumetric flow rate. So recall that the equation, or the continuity equation, Q is equal to AV, or the flow rate equation, still holds true. So we have this Q, that's the volumetric flow rate, that's in cubic meters per second, and this one is the cross-sectional area, let's say this is meter squared, and this one is the velocity, this is meters per second, so that's why it's meter cube per seconds. But the difference is that for the velocity, how do we compute the velocity in open channel is we use the Manning's equation. Alright, so let's do this. So first solution, first step is to, let's just list down necessary informations. So we have this depth y, is equal to 2 meters. We also have the the bottom width B, that's 3 meters. We also have the S. The slope is, it says 2 meters rise, that's 2 meters divided by 1000 meters. So that's a unit of length per unit length, so therefore it has no units. So if you simplify this is 0.002. And for the N, let's go to the table. It says that we are having a channel made up of um, concrete finished concrete, so that means it has a finished a smoother surface. So we have this Mannings coefficient of 0.012. So if you compare this, by the way, if you can compare this unfinished and this finished concrete, you can see that we have a smaller value for a smoother surface as compared to a rougher surface. So the more rough the surface, the higher our number um, for our Mannings coefficient. Alright, so here's our value 0.012. So n is equal to 0.012 from table 11-5. Right, so that's it. Then, since we know that the working equation is just Q is equal to AV, then let's just solve for V. However, for V, we need, right, for V, we need to solve for the hydraulic radius. So let's just take this one step at a time. RH is solved for RH, that's the hydraulic radius. RH is just equal to A divided by the wetted perimeter. So our area, since it's just a rectangle, that is 2 times 3. Then of course that's going to be meters squared. 2 meters by 3 meters, that's meters squared, divided by the wetted perimeter. So the wetted perimeter is the perimeter of the of the perimeter of um, the wetted boundaries. All right, wetted boundaries. So it's this 2 plus 3 plus 2. So that's 5 plus 2, that's 7. So this is 7 meters. And if we compute this, so this is 6 divided by 7. This is 0.86. And 0.86, this is meters. Okay, so next step, let's solve for, or let's apply. Let's apply the Mannings equation to solve for to obtain velocity. Okay, so here's our equation. V is equal to 1 all over n, r raised to 2/3, s raised to 1/2. Our n is 0.012 times our r, that's 0.86 raised to 2/3, or 0.67. And this one is 0.002 raised to 1/2, and this is 0.86 0.86 raised to 2/3 times 0.002 raised to 1/2. What else? Divided by 0.012. So this is 4.12. Or let me do it again. 1 all over 0.012 and times 0.86 raised to 2/3 times 0.002 raised to 1/2. This is 3.37 meters per second. Okay, so that's it. And since we have the V, we also know the A, then uh, so solving now for the flow rate. So the flow rate is just equal Q is equal to AV. Then our A is just 2 times 3. That's just the cross-sectional area, 2 times 3. And this is also times 3.37. This is equal to 3.37 times 2 times 3. That's 20.22. Right, so 20.22 cubic meters per second. Right, so that's our flow rate. Okay, so then next one is we'll do another problem regarding this Mannings equation. Okay, so next problem is we this one is taken from our another reference text, Applied Fluid Mechanics by Mott and Turner. It says here that design a rectangular channel to be made of formed and finished concrete to carry 5.75 cubic meters of water when laid on a 1.2% slope. The normal depth should be 1/2 of the width of the channel bottom. So this one is design. Basically, when you say design, it's just we are trying to size up the channel based on the loadings that we have. So, but the basic equation is just the same. So for the solution, then first let's obtain or list down necessary information. So it says that our normal depth, that's this, y is equal to b all over 2. That should be, actually the normal depth is not this one. It seems that this is not this one, but let's just say this is this. All right, so our y is b all over 2, and our b is, of course, that's just simply b. And what else? The flow rate, the flow rate is q is equal to 5.75 cubic meters per second, and the s is 1.2. That's 1.2% slope, and that means 1.2% divided by 100%. That is 0.012. And for the Mannings coefficient, this is unfinished concrete. Then we'll use this 0.015. So n is equal to 0.015 from table 11 dash 5. Right, so that's our informations. And now let's try to apply the flow rate equation and the Mannings equation. By the way, if the flow rate equation is q is equal to AV, and V, and the Mannings equation is V is equal to, and V is equal to 1 all over n r raised to 2/3 raised to s raised to 1/2, then that means if we combine this, what we get is q is equal to 1 all over n times the area, right? That's the area, times r raised to 2/3 s raised to 1/2. So here's gonna be our flow rate equation with Mannings coefficient. Sorry, with Mannings equation. Okay, so let's do that using flow rate equation and Mannings equation. So this is q is equal to 1 over n times a times r raised to 2/3 s raised to 1/2, and of course r, we know that r is equal to area divided by the wetted perimeter. So that means 2/3 plus 1, that's 2/3 plus 1, that's 5/3. or let's just leave it as it is. Or no. Uh, Let us write it in this form: 1 all over n a times a all over the wetted perimeter, that's 2/3, okay, times s raised to 1/2. Right, so what is a is just simply b all over 2. This is it, b all over 2 times b, which is equal to b squared all over 2. So that's our a. Right, so if we substitute, and our wetted perimeter is equal to b all over 2 times 2, right? Because b all over 2 plus b all over 2 plus b, so this is equal to 2b. b plus b, so that's 2b. Alright, so let's substitute now. So q is equal to 1 all over 0.015, and our area is b squared all over 2 times our hydraulic radius of b squared all over 2 divided by, let's write it, b squared all over 2 divided by 2b raised to 2/3. And what else? We have s of 0.012 s raised to 1/2. Right, so let's do the computation. Let's try to solve this. 1 all over 0.015 times alpha x. Sorry, let's substitute this. Since we have the value of q, this is 5.75 cubic meters per second. Right, so here's our equation. We have one unknowns, then we can just use the shift solve command. This is 5.75, so alpha equals, okay, 1 all over 0.015 times, so here's our variable, that's alpha, let's just use alpha x, times alpha x squared sorry all over 2 times, and we have this b squared alpha x squared divided by 4b. 4, actually we can simplify that if you like, 4b alpha x, then this one is raised to 2/3, and times 0.012 raised to 1/2 or 0.5, then shift solve. So we have I think we have 1.67 or 68, 1.68 meters. So if that's our our bed width, then our depth would be uh, y is equal to b all over 2. So this is divided by 2. This is just 0.83 meters. Right, so that's it. Okay, next one, we'll do another problem. This is problem number 3, and we have this cross section, trapezoidal cross section, and again this one is still taken from our reference text, Applied Fluid Mechanics, Says here, calculate the minimum slope on which the channel shown in the figure must be laid if it is to carry 50 cubic feet per second of water with a depth of 2 feet. The sides and bottom of the channel are made of formed and finished concrete. Okay, so here's our bottom width, here's our top width, and here's our depth. So now let's solve. So first for the solution, let's obtain or list down obtain necessary information. So our Q, this is 50 cubic feet per seconds, and our Y is 2 feet. Our top width T, or capital letter B if you'd like, T is equal to 8 feet, and our bottom width is 4 feet. And our slope is, of course, that's what we are asked to solve for. And for the value of n, this is unfinished concrete, so that's 0.015. Right, so now um, let's apply the Mannings equation for to solve for the velocity. However, we also need the need the area. We also need the wetted perimeter, right? So for the area, it's b plus y times y. So let's go to our table. Right, so for the trapezoidal area, that's b plus y times y, and here's our wetted perimeter. Right, so for the area, b plus y times y. So what's our b? That's the bottom width. That's 4. 4 plus, what's y? 4 plus 2 times the value of y again. So 4 plus 2 times 2. And this is 4 plus 2, that's 6 times 2, that's 12 feet squared. For the wetted perimeter, this is b plus 2y times this w, but this w is equal to square root of 1 plus t squared. So b plus 2y times the square root of 1 plus t squared. The value of t should be this one. So what's the t right here? Okay, so this one is, we have here 4, so 8. So first we need to analyze. So that means that if this is 4, right, if this is 4, then this one would be 2, and the other one right here would be 2, right, because the total top width is 8. So 4 plus 2 plus 2, that's 8, and for our height, this is also 2, because that's already given. So 2 over 2, this is just actually our t, this vertical. So t is just equal to 2 all over 2, then that just means it's just 1, right? So our t is 1. So let's substitute the value. So for b, this is 4 plus 2 times the y, the flow depth of 2, times the square root of 1 plus t squared. So 1 squared is just that's just 1. So 1 plus 1, this is just 2, square root of 2. And let's calculate this. This is square root of 4 plus 2 times 2 times square root of 2. This is 9.65. So 9.65 or 66 feet. Alright, so that's our area. Here's our wetted perimeter, and now let's solve for the hydraulic ranges. RH is equal to area divided by wetted perimeter, and this is 12 divided by 9.65 or 66. This is 66. 12 divided by 9.66. This is 1.24. 1.24 feet. Okay, so next one is we have this. Then I think we can now solve for the Mannings equation. So substituting. Okay, so recall this is Q is equal to, V is equal to 1 all over N times R raised to 2/3 times S raised to 1/2. We have this, we have R, we have V. Oh no, Q. So it should be, sorry. So let's do this again. Once again, Q is equal to 1 all over N times area times the R raised to 2/3 S raised to 1/2. So we have R, we have A, we have N, and we have Q, and therefore we can solve for S. So let's substitute all the values. We have 50 feet cubed per seconds, and this one is 1 all over 0.015. And for the area, this is 12. For our area, this is 12 feet squared. So 12 feet squared. And for the R, this is 1.24 feet. It's 1.24 feet raised to 2/3 and S raised to 1/2. Right, so therefore S is equal to, let's do the shift solve, 50 equals 1 all over 0.015 times 12 times 1.24 raised to 2/3 times our variable, let's say x, alpha x, raised to 1/2 or 0.5. Right, so shift solve. Okay, so it takes time. Our value for S is equal to 0.0029. Right, so that's our slope. Okay, so if we review what we did, is just simply we are just using the Mannings equations and the flow rate equations, and if we encounter a geometry, a more complex geometry compared to rectangle, then we just go to the tables and then apply the equations for the specific dimensions. Okay, so that's it, and we solve this. We solve the area, we solve the wetted perimeter, and then we can solve the hydraulic ranges. And if you have all that, then you can solve for the, you can apply this combined flow rate and Mannings equation. Okay, so I think um, we still need to do another problem, but I think we'll just do that in the next video.